welcome to the Deep Dive. Today we are opening, well, a vast stack of source material. It doesn't just chronicle a great scientist, but really a figure who lived right there at the absolute crossroads of fundamental physics, philosophical reality, and global destiny. Niels Bohr.
That's right. And for many people, Bohr is kind of a single iconic image, isn't he? You know, the famous planetary model of the atom, the simple diagram of electrons orbiting a nucleus that you see, well, everywhere, t-shirts, textbooks.
Yeah, that simple picture.
But that picture, it's really just the foundation. Our mission today is much larger. We're examining Bohr's life through, let's say, 3 distinct and equally impactful lenses. We see him first as this revolutionary scientific founder.
Okay.
Second, as a philosophical combatant, someone who really wrestled with Albert Einstein over the very definition of reality itself.
A huge debate.
Huge. And third, as a statesman, which is maybe the most surprising part, an unexpected and relentless political crusader for what he called an open world, right at the dawn of the nuclear age.
Yeah. It really is a remarkable progression. And what's so striking, I think, is how quickly his initial work established his reputation. We found this initial nugget of knowledge just to frame that impact. Bohr was recognized very early on. He received the Nobel Prize in Physics in 1922.
Right, 1922.
And that was for his quantum model of the atom, an idea he'd published almost a full decade earlier, back in 1913.
Think about that timeline for a second. He basically turns atomic physics upside down as a young man. And then the next decade, he spends it building his institute, attracting the world's best minds, and arguing about the philosophical implications of the very structure he'd discovered. He didn't just propose a theory, he really launched a whole new branch of human inquiry.
Okay, let's unpack this monumental first chapter then. To really appreciate why Bohr's work in 1913 was so revolutionary, we have to get a handle on the magnitude of the problem he solved, this stability problem. What was classical physics telling us about the atom just before Bohr stepped in?
Well, the essential framework was kind of already there, thanks largely to Ernest Rutherford's work on alpha-ray scattering. Rutherford had shown that the atom was mostly empty space, right?
Right.
Containing this tiny, massive, positively charged nucleus with electrons surrounding it. It looked, for all intents and purposes, like a miniature solar system.
Classic image.
Exactly. The problem was, under the rules of 19th century classical electromagnetism, that structure was impossible. It couldn't exist.
Help us understand that contradiction. Why couldn't that solar system atom exist according to the old rules?
It comes down to Maxwell's equations. An orbiting electron is constantly changing direction, which means it is constantly accelerating. And classical electrodynamics states quite unequivocally that an accelerating electric charge must continuously radiate energy. It has to, in the form of electromagnetic waves.
So if the electron is radiating energy away, it's losing energy, it's slowing down, spiraling.
Precisely. If it's continuously losing energy, the electron would inevitably spiral inward, pulled towards the positively charged nucleus. And the calculation showed this collapse would happen in a staggeringly short time. We're talking picoseconds, like poof.
Wow.
So if classical physics was the final word, every single atom in the universe should have immediately collapsed. The entire physical world, including you and me, shouldn't exist. The very foundations of matter were theoretically unstable.
So Bohr steps in to basically save the atom. But he can't save it using the old rule book. He has to introduce a fundamental break, what he called the essential discontinuity.
That phrase itself is it's a beautiful piece of intellectual violence against classicism, isn't it? Bohr recognized that the atomic process involved these sudden, discontinuous leaps, these quantum jumps, which were, in his words, completely foreign to the classical theories. He was forced to basically abandon the demand for causality and continuity that classical physics held so dear.
And this leads directly to his famous quantum postulate. What did that discontinuity actually dictate about how the atom behaves?
The postulate stated 2 core things, really. First, atoms exist only in specific, defined, stationary states with fixed, discrete energy levels. As long as the electron stays in one of these allowed orbits, it does not radiate energy.
Which flatly contradicts Maxwell.
Totally contradicts Maxwell. Second, light, or more accurately, a quantum of energy, is only emitted or absorbed when an electron transitions between these fixed stationary states. It jumps, you see, from one level to another. It doesn't continuously radiate energy during the process.
He essentially just decreed stability into existence by saying these states exist and they don't radiate. But decrees need some mathematical backing. How did he mathematically lock down which orbits were allowed and which weren't?
Well, this is where his genius in synthesis really shines. He introduced the crucial mathematical hypothesis, the quantization of angular momentum. He stipulated basically that the angular momentum of the revolving electron must be equal to n times h divided by 2.
Okay, let's break that formula down a bit for the listener. N times h over 2, Carol.
Right. The key variables are simple but incredibly profound. H is Planck's constant, which is the fundamental unit, the basic currency of energy quantization that Max Planck had introduced earlier.
Yeah.
And n is just an integer 1, 2, 3, and so on. It's a quantum number. So because the angular momentum has to be a whole multiple of that fundamental quantum unit, the H2 part, the electron simply cannot occupy any old arbitrary orbit. Only those discrete numbered orbits are allowed.
So it quantizes the allowed paths.
Exactly. And he connected this entire hypothesis directly to Planck's earlier theory of radiation. It wasn't really a derivation from first principles. It was more a clever revolutionary integration of existing quantum ideas into the actual structure of the atom.
And what's really fascinating, what makes it so compelling, is that this radical, completely counterintuitive idea immediately led to massive predictive success. It wasn't just like abstract philosophy. It worked.
Oh, the experimental successes were stunning and almost immediate, especially for the simplest atom, hydrogen. The theory accurately predicted the specific wavelengths of light emitted by hydrogen, what we call the famous Balmer series.
Which people had seen but couldn't explain, right?
Precisely. Before Bohr, the Balmer series was just the set of observed spectral lines that happened to fit a rather peculiar empirical formula someone had cooked up. Bohr's model explained why that formula worked. It showed the lines corresponded to electrons jumping from higher energy levels, higher in values, down specifically to the second energy level, N2.
It turned an empirical observation into a theoretical explanation. What other successes helped validate this completely new quantum logic?
Well, the theory successfully explained the general spectra of elements, not just hydrogen, though less precisely for more complex atoms. It also explained ionization processes, how atoms lose electrons when hit by ultraviolet light or X-rays. And crucially, it provided the exact same mathematical expression for the kinetic energy of an electron ejected in the photoelectric effect.
Which is T equals high minus W.
Exactly that equation. 2T equals Hase-Norable. The same one that Albert Einstein had deduced a few years earlier using his idea of light quanta, or photons.
Wow. So it connected Bohr's work on the atom's internal structure directly with Einstein's completely different work on the nature of light itself.
Yes. It was one of those beautiful moments in physics where previously disconnected corners of the field suddenly click together. It showed this quantum idea was really fundamental.
So we have this wildly successful model. It wins him the Nobel Prize. It explains things nobody could explain before. Yet we know that modern physicists don't actually use the Bohr model for serious calculations anymore. Why is the Bohr model, for all its revolutionary success, considered merely a stepping stone today?
It's a bit like the difference between, say, a good roadmap and a highly detailed satellite image. The Bohr model introduced the absolutely essential core concept. Discrete energy levels are real, quantum jumps are real. That was the revolution.
Right.
But, as we sort of hinted in the learner's takeaway section of our notes, it's still taught today, much like Newtonian mechanics is still taught. Why? Because it offers pretty good predictive value within a certain limited range, and honestly, it's intuitively much easier to grasp than the full quantum mechanics that followed.
You used an analogy earlier, something about a yardstick versus a micron stick.
Right. If you're building a doghouse, a simple yardstick works perfectly fine. You don't need nanometer precision. But if you're designing, say, a high-precision microinstrument or understanding complex chemical bonds, you need the full, dense mathematics of wave mechanics, Schrödinger's equation, and all that. The Bohr model's elegant simplicity hides some profound limitations that actually became clear almost immediately.
What were those really fundamental limitations that forced physics to move beyond Bohr's initial picture?
Well, the biggest one was that the model could only accurately calculate the spectrum for atoms with one single electron. Things like hydrogen or helium that's lost one electron, so it's ionized helium.
So only the simplest cases.
Only the very simplest. It completely failed to explain the spectra of multi-electron atoms, which is, most of the periodic table. The
Right.
interactions between multiple electrons just weren't handled properly. And even more tellingly, it started to break down when you looked closely at how atoms behaved in external fields.
You mean things like the Zeeman effect and the Stark effect?
Exactly. When you place an atom in a strong magnetic field that's the Zeeman effect, or an electric field, the Stark effect, the spectral lines you observe actually split into several distinct finer lines. This fine structure requires accounting for much more subtle interactions between electrons, their intrinsic spin, and how the external field affects the complex internal energy states.
And the simple circular orbits of the Bohr model just couldn't handle that complexity.
Not at all. It required a much deeper quantum understanding. People like Sommerfeld introduced elliptical orbits, which helped a bit. But eventually, physicists had to abandon the idea of fixed orbits altogether, replacing them with these fuzzy probability clouds described by wave functions. The electron isn't in an orbit. It exists as a probability distribution around the nucleus.
So it sounds like Bohr designed this crucial first quantum ladder, but almost immediately realized that reaching the higher rungs required a completely different kind of wood, so to speak. And this realization, this inherent weirdness, pushed him out of just doing physics calculations and into a new realm, epistemology, the philosophical core of quantum mechanics.
Yes, that fundamental weirdness of the quantum jump, that essential discontinuity he talked about, meant Bohr had to abandon more than just Maxwell's laws. He had to let go of a really deep classical assumption. The idea that observation is just a passive act, something that happens to a system from the outside without affecting it.
And this led him directly to his defining philosophical doctrine, the principle of complementarity. How did he officially define this, well, really revolutionary idea?
Bohr defined complementarity as the recognition that, in quantum theory, the classical demands we usually make, like knowing the exact space-time coordination where something is and when, and also claiming causality, predicting exactly where it will go based on forces, these two things are features of our description that are, and this is the key phrase, complementary but exclusive.
Complementary but exclusive.
Yeah.
Okay, that sounds like a fundamental tension built right into the fabric of reality itself, or at least our description of it. It forces us to choose how we look at something.
It is a truly radical departure from classical thinking. And Bohr justified this tension because, he argued, the very act of observing an atomic phenomenon necessitates an unavoidable and crucially non-negligible interaction with the agency of observation. Your measuring device isn't separate, it becomes part of the system you're measuring.
So because you can't ignore the measuring device's effect, you can't really assign an independent reality to the phenomenon completely separate from your act of measuring it.
That's exactly his point. The properties you measure don't really exist in a definite state before you measure them. The measurement itself helps bring them into being, but in doing so, it necessarily disturbs other potential properties.
Let's maybe try a simple non-physics analogy just to help frame this rather abstract tension. Imagine you're trying to describe, say, the culture of an organization.
Okay.
You could focus on the formal hierarchical structure, the org chart, the written rules. That's like your space-time coordination, the static picture. Or you could focus on the dynamic interpersonal relationships, the informal networks, how decisions actually get made day to day. That's more like the causality, the dynamics.
That's actually a pretty good analogy. Both descriptions are necessary to understand the organization fully, right? But the very act of, say, strictly enforcing the written hierarchy might stifle or change those informal causal dynamics you're trying to observe. Similarly, in quantum mechanics, if you design an experiment to precisely pin down an electron's position, its spacetime coordinates, the very nature of that measurement inevitably disturbs its momentum, making its future path, its causality, fundamentally uncertain. You gain sharpness in one description, but you inherently lose sharpness in the complementary one.
The most famous, most concrete physical example of this is wave-particle duality.
Absolutely. That's the classic example. The electron sometimes behaves like a localized particle, like a tiny billiard ball, which lets us measure its position. But other times, in different experiments, it behaves like a spread-out wave, showing interference patterns just like light waves do.
Which is totally contradictory in classical terms. A thing can't be a localized point and a spread-out wave simultaneously.
Not in the classical world, no, but in the quantum world, both descriptions are necessary to fully characterize the electron's behavior. They are complementary aspects. And crucially, the specific experimental setup you choose actually determines which aspect, which complementary reality particle or wave you observe.
We mentioned in our research that Bohr's commitment to this whole philosophy wasn't just, academic papers. He actually had a personal symbol representing it.
He did, yeah. It's quite telling. When he was knighted by the Danish king in 1947, he had to choose a coat of arms. He chose the ancient Chinese symbol, the Taijitu, the yin and yang symbol.
Ah, the circle with the black and white swirling shapes.
Exactly. That image of dynamic opposites existing in this balanced, interwoven harmony. And the motto he chose to put beneath it was the Latin phrase, contraria sunt complementa.
Which means?
Opposites are complementary. He literally framed his life's philosophical work, his whole worldview, around this profound idea of embracing necessary paradox, of holding contradictory truths together.
Which naturally, inevitably leads us to the great intellectual drama of the 20th century. The Bohr-Einstein debate. This wasn't just some academic squabble between colleagues, was it? It was this decades-long clash over whether quantum mechanics, particularly Bohr's Copenhagen interpretation, was the final word on reality.
Oh, it was a marathon, not a sprint. It really spanned from the famous 1927 Solvay conference through all sorts of ingenious thought experiments they threw at each other, right up until Einstein's death in 1955. Einstein was just deeply, fundamentally uncomfortable with the Copenhagen interpretation, which Bohr championed. Einstein clung to the belief that there must be an underlying, objective reality that exists independent of whether we observe it or not.
We often hear Einstein's famous line about God not playing dice with the universe. So was his main sticking point the uncertainty principle, the inherent randomness and indeterminacy?
Well, that was definitely part of the initial skirmish, yes. He hated the probabilistic nature of it. But modern analysis of their long dialogue, looking back at their letters and papers, suggests that Einstein's chief source of discomfort, the thing that really bothered him, was actually something even weirder and deeper: entanglement.
Ah, the spooky action at a distance.
That's the one. He recognized very early on that the quantum realm fundamentally failed the classical notion of mutual independence of interacting systems. Once two quantum systems interact, they can remain connected in this bizarre way no matter how far apart they fly.
Okay, let's dedicate a bit of time to the source of that discomfort, probably the most famous chapter in their debate, the EPR paradox.
Right. The EPR paradox, named for Einstein, Podolsky, and Rosen, who wrote the paper in 1935. It was this brilliant thought experiment designed specifically to show that quantum mechanics must be an incomplete theory, that it couldn't be the whole story.
Okay, how did it work?
They imagined creating two quantum particles, say two electrons, that are linked together in a specific way. They're entangled. Their properties, like spin, are correlated. Then you let these two particles fly off in opposite directions, potentially miles apart.
Okay, far apart but still linked.
Still linked, according to quantum mechanics. The theory dictates that their properties remain perfectly correlated. So, if you measure a specific property, like the spin on particle A, you instantly know the corresponding property of particle B, no matter how far away it is. Instantly.
And that instantaneous connection, faster than light, violating locality, was what Einstein couldn't accept.
Exactly. For Einstein, this spooky action at a distance was simply unacceptable. It violated the principle of locality, a cornerstone of his theory of relativity, which states that no influence can travel faster than the speed of light. He argued that since no physical signal could travel instantly between A and B, the only way particle B could know what happened to particle A was if both particles carried some kind of predetermined objective properties, local hidden variables, right from the start, before any measurement took place.
Properties that dictated the outcome of the measurement beforehand.
Right. And since standard quantum mechanics does not include these hidden variables, it says the properties aren't definite until measured weight. Einstein concluded that the quantum description must therefore be incomplete. It was missing something real.
So how did Bohr respond to this ingenious challenge?
Bohr's response was classic complementarity, really. He essentially attacked the premise of the EPR argument. He argued that their fundamental assumption that the two particles could be considered as having separate, independent realities after they had interacted and become entangled was simply false in the quantum context.
Because they were entangled, they weren't separate anymore?
Precisely. They formed a single, inseparable quantum system, even when miles apart. The moment you perform a measurement on particle A, you're interacting with the entire entangled system. You can't isolate particle B and talk about its independent properties anymore. For Bohr, entanglement, this profound failure of mutual independence, isn't a paradox pointing to incompleteness. It's actually the very premise from which complementarity itself is derived.
So the instrument and the object are linked in measurement, and the two entangled particles are linked across space. You can't chop reality up into purely independent bits in the way classical physics assumed.
That's the core of Bohr's view. You cannot ascribe independent reality to the components of an entangled system once they have interacted. The system has to be considered as a whole.
So the ultimate takeaway here for you, the listener, is that this huge debate wasn't really solved by pointing to a calculation error. It came down to a fundamental choice about what you accept as reality. Do you prioritize locality, like Einstein, and assume quantum mechanics is incomplete? Or do you prioritize the completeness of the quantum description, like Bohr, and accept non-locality and complementarity as fundamental features of the universe?
And it's fair to say that the subsequent history of physics, especially with experiments confirming the predictions of entanglement, like Bell's theorem tests, has largely sided with Bohr's view. Quantum mechanics, as strange as it is, seems to be the most complete description we have, even with its spooky connections.
Now, Bohr's scientific and philosophical revolutions didn't just happen in his head or on paper. They happened in a real place, the Institute for Theoretisk Physik in Copenhagen. This institute became really the global nucleus for quantum physics in the 20s and 30s.
Absolutely. The Institute's founding, which was officially inaugurated in March 1921, was actually front-page news in Copenhagen. It was a genuine moment of national pride. But getting there, the path to that inauguration was apparently quite fraught with difficulty, reflecting the intense economic instability across Europe after World War I.
Yeah, we noted in the sources that the actual construction took over 2 years, and the final cost overruns were pretty substantial.
They were significant, yes. Severe inflation of the Danish krone caused major delays and drove costs way up. It was actually so disruptive that Bohr was forced to cancel the original plans for Ernest Rutherford, the man who discovered the nucleus, Bohr's own mentor, to come and perform the official opening ceremony.
Wow, imagine that disappointment. Not having the discoverer of the nucleus open the institute dedicated to understanding its structure.
It must have been profound, and it really underscores just how fragile the whole scientific enterprise was in post-war Europe. Funding was tight, economies were shaky.
And the physical building itself seemed to reflect Bohr's ambition and maybe his life. It wasn't just a lab complex, was it? It was literally his family's home, too.
It really was a testament to his dedication, and it reflected his dual life perfectly. The top 2 floors served as the actual residence for Niels, his wife Margrethe, and their 6 sons. Apparently, they often hosted visiting scientists overnight, right there in the family apartment.
Like a boarding house for geniuses.
Kind of. And meanwhile, the ground floor and the basement housed all the essential research infrastructure. Specialized laboratories, offices for the theorists, the main lecture theater, and, critically, a well-equipped workshop for building the precision instruments they needed.
You mentioned Margrethe. We should pause on her role because the source material we looked at credits her as being far more than just a supportive spouse.
Yes, Margrethe Nerlin Bohr was widely described, even by Bohr himself, as his most trusted advisor. She wasn't a trained physicist, that's important to note, but she apparently served as his crucial intellectual sounding board. He would talk through his complex arguments and theories with her, and she helped him clarify his thinking, sharpen his explanations. It sounds like it was a true partnership of intellectual equals, in terms of rigor, if not specific expertise.
That's fascinating. And the Bohr legacy didn't stop there, did it? Their family was quite remarkable.
It really was. Their son, Niels Bohr, followed directly in his father's footsteps. He became a distinguished physicist himself and actually won his own Nobel Prize in Physics in 1975, sharing it for work on the structure of the atomic nucleus, building on his father's legacy.
Incredible.
And even Niels's older brother, Herger Bohr, was a distinguished mathematician. And rather surprisingly, he was also an Olympic footballer who played for Denmark. Quite the talented family all around.
Absolutely. Now, such monumental scientific endeavors like building this world-leading institute require monumental funding. And Bohr seems to have been relentless in seeking support, especially from outside Denmark.
He absolutely was. He recognized very early on that relying solely on strained European funding sources wasn't going to cut it. So he traveled to the United States and made crucial contact with the International Education Board, the IEB.
And the IEB was connected to Rockefeller money.
Yes, it was part of the huge Rockefeller philanthropy empire, and its specific charter was to promote and advance education and science outside the U.S. Bohr saw an opportunity.
And this American money clearly played a huge role in fueling the quantum revolution happening in Copenhagen.
It was absolutely critical, both for expanding the institute physically and for enabling collaboration. The IEB funded the institute's major expansion projects in the mid-1920s, but perhaps even more importantly, it provided the lifeblood of global science at the time, fellowships for visiting scientists.
Bringing minds together.
Exactly. In one period mentioned in the sources, the IEB provided funds for 15 out of 63 visiting scientists. That's almost a quarter, more than any other single funding source. This allowed brilliant, but often financially struggling young theorists from all across Europe and beyond to come together in Copenhagen, to argue, to collaborate, to spark ideas off each other.
What about key Danish support? Was there local funding too?
Yes, domestically they relied heavily on the Raskersted Foundation. This foundation was named after two prominent Danish figures, Rasmus Rask, a comparative philologist, and Hans Christian Ørsted, the physicist famous for discovering electromagnetism.
Interesting combination, linguistics and physics.
It is, isn't it? And the foundation was specifically established by the Danish government to promote international scientific exchange by supporting foreign scientists visiting Denmark. The very naming of it, linking language and physics, seems quite thematic, almost mirroring Bohr's own philosophical efforts to bridge disparate fields of knowledge.
But the truly important historical role of the Institute, perhaps beyond even the science done there, wasn't just its funding, but its function as a kind of diplomatic sanctuary during a period of massive international scientific schism.
This is a crucial point, and it's often overlooked in just telling the scientific story. After World War I, many of the newly formed international scientific organizations, like the International Union of Pure and Applied Physics, which was founded in 1922, actually imposed a political agenda. They quite hypocritically excluded physicists from the defeated Central Powers, Germany, Austria, Hungary.
So the global scientific conversation was literally split down the middle by post-war politics.
Precisely. And this created a profound, incredibly damaging schism. We're talking limited journal exchanges, scientists being barred from conferences, and virtually no personal contact allowed between the scientists from the former Allied nations and those from the Central Powers. It was terrible for the progress of science.
And then Denmark offered a way around that.
Exactly. Denmark had maintained its neutral status throughout the war. That neutrality, combined with Bohr's immense personal reputation and integrity, made his institute in Copenhagen the only truly neutral essential meeting ground. It was a place where German physicists like Heisenberg could freely interact with British, French, and American physicists.
He effectively fostered intellectual complementarity on a geopolitical scale, forcing former enemies, or at least scientists from enemy nations, to collaborate on the strange new physics.
You could absolutely see it that way. It was vital for the field's advancement. And the list of collaborators who passed through Copenhagen during that golden era reads like a future Nobel Prize winners list. Werner Heisenberg, of course, who visited frequently between the 1920s and 1940s and became a key architect of matrix mechanics right there. Wolfgang Pauli, famous for the exclusion principle, was a close friend and frequent correspondent, often hashing out ideas with Bohr. George de Hevesy, who later won the Nobel in Chemistry in 1943 for his work on isotopes, worked closely with Bohr at the Institute, too. Copenhagen was truly the vibrant collaborative heart that nurtured almost all the revolutionary quantum concepts we're discussing today.
Then, around the mid-1930s, the focus of the Institute, and indeed much of physics, shifted dramatically. It moved from the perhaps more abstract theories of quantum mechanics surrounding the electron clouds to the terrifying realities hidden within the atomic nucleus itself. And this pivot had, well, earth-shattering consequences.
Yes, Bohr very quickly pivoted his institute's focus and resources towards the emerging field of nuclear physics. He didn't just follow the trend, he established Copenhagen as a pioneering institution in this new domain too. He developed or co-developed two really foundational theoretical models that helped explain how the nucleus behaves, especially when it's undergoing some kind of transformation or reaction.
Okay, let's start with the first one, the compound nucleus model, which he developed around 1936. What was that about?
This model addressed the question of how nuclear reactions actually proceed. Before Bohr's idea, many physicists kind of assumed that an incoming particle, say a neutron, hitting a nucleus, would interact directly and almost instantly with just one particle inside that nucleus, maybe knocking it out.
Like a billiard ball collision.
Sort of, yeah. Bohr argued differently. He proposed that reactions proceed through a temporary intermediate state, what he called the compound nucleus. The idea was that the incoming energy from the particle would first be rapidly absorbed and shared among all the nucleons, all the protons and neutrons inside the nucleus, like a drop of water, absorbing the energy of a small splash and getting agitated.
Okay, so it's not a one-on-one collision, it's the whole nucleus getting excited together. Why was that intermediate state concept so important?
Because it meant that the subsequent decay or reaction of that nucleus, what particle gets emitted, for instance, wasn't really dependent on how the initial particle came in. It only depended on the total energy level and properties of that shared, temporary, agitated compound nucleus state. It became a probabilistic model. The nucleus forgets how it was formed and just decays based on its current excited state. And this model turned out to be very successful in explaining many experimentally measured nuclear cross-sections and reaction rates.
Interesting. And then came the model that really helped explain the mechanism of the atom bomb itself, the liquid drop model.
That model, which he developed together with the American physicist John Wheeler in 1939, was directly applied to understanding the newly discovered phenomenon of nuclear fission. They treated the nucleus, by analogy, as if it were an incompressible liquid drop, held together by the strong nuclear forces, acting kind of like surface tension in a water droplet.
How does that liquid drop analogy actually help us understand fission, the nucleus splitting apart?
Well, fission is literally the nucleus splitting into two or more smaller pieces. The liquid drop analogy provided a really useful mathematical framework for visualizing and calculating this. If you imagine injecting energy into this liquid drop, say, by hitting it with a neutron, the drop starts to oscillate, to wobble.
Okay.
If you inject enough energy, the oscillations can become so violent that the surface tension, the nuclear force holding it together, is overcome. The drop stretches out, maybe into a kind of dumbbell shape, and then snap. It breaks apart into two smaller, highly energetic fragments, releasing a huge amount of energy in the process. It looks a bit like a biological cell undergoing division.
And their key paper on this, The Mechanism of Nuclear Fission, provided the theoretical basis for this process just as the world was waking up to it.
The timing is absolutely incredible, isn't it? This detailed theoretical work explaining how fission works was published right as the experimental discovery was sending shockwaves around the globe, both scientifically and politically.
And those shockwaves were felt very quickly in the public sphere.
Oh, absolutely. The initial discovery, which was credited largely to Otto Hahn and Lise Meitner, though Meitner's contribution was initially overlooked due to her forced exile, sparked immediate global alarm. We found reports in the New York Times from January 1939 talking about an atom explosion, freeing an unprecedented 200 million volts of energy.
200 million volts.
A staggering number at the time. And by April of that same year, 1939, the public rhetoric was escalating dramatically. We saw headlines literally proclaiming things like, "Vision Earth rocked by isotope blast. Scientists say bit of uranium could wreck New York." The destructive potential was immediately, terrifyingly clear, even if the path to achieving it wasn't yet obvious.
This rapidly escalating situation brings us to probably the most debated, heavily scrutinized, and ultimately ambiguous moment in Bohr's entire life. The controversial meeting with Werner Heisenberg in occupied Copenhagen in September 1941. This single event has been the subject of plays like Michael Frayn's Copenhagen, countless documentaries, and endless historical arguments.
Yes, and here we must be really careful to report only on the facts that are contained within the sources available, including the documents that were eventually released by the Niels Bohr archive in 2002. So Heisenberg, Bohr's former student and collaborator, visited Bohr in Nazi-occupied Copenhagen in September 1941.
A very dangerous time and place.
Extremely. And it's critical context to remember that at that specific point in 1941, Bohr apparently did not believe that an atomic bomb was practically possible in the foreseeable future. He viewed the challenges, especially separating the needed uranium-235 isotope, as scientifically and industrially insurmountable on any reasonable timescale.
So their meeting occurred under this shadow, but also with a potentially massive difference in their perceived stakes or perceived feasibility of a bomb.
Absolutely. Now, Heisenberg, much later in his autobiography, claimed that he traveled to Copenhagen partly to signal to Bohr, his mentor figure, that he and other German scientists were perhaps trying to prevent the Nazi regime from actually obtaining a nuclear weapon, or at least slow down the effort, maybe by overestimating the difficulties.
That was Heisenberg's later account.
That was his later account. However, the available contemporary sources, including Bohr's own unsent letters drafted after the war, indicate that Bohr's reaction during and immediately after the meeting was one of profound shock, anger, and deep upset.
Why the anger, according to Bohr's perspective?
From Bohr's perspective, as reconstructed from those later drafts, he felt Heisenberg was not coming to him for counsel on how to sabotage the German effort. Instead, Bohr perceived that Heisenberg was perhaps probing him, maybe asking for Bohr's moral blessing, or even indirectly seeking technical hints or confirmation about the feasibility of Germany's bomb program. Bohr seemed to feel Heisenberg was suggesting Germany could win the war with such weapons.
A completely different interpretation of the conversation's intent.
A completely different and deeply disturbing interpretation for Bohr. The conversation itself was apparently quite terse, possibly confused by the dangerous circumstances and the need for veiled language, and it ended very poorly, abruptly cutting short Bohr's long and deep relationship with Heisenberg.
And the documents released in 2002, did they clear things up?
Unfortunately, no. The documents relating to the meeting, which were highly anticipated when finally released by the Niels Bohr archive, mostly consisted of Bohr's own later drafts of letters attempting to recount the meeting. While they powerfully convey Bohr's negative reaction and interpretation, they don't definitively resolve the fundamental ambiguity of what Heisenberg truly intended to convey, or even what Bohr precisely understood Heisenberg to be saying at that exact moment in 1941.
So it remains this historical Rorschach test almost, a mystery of intent, clouded by wartime secrecy, the trauma of occupation, personal anguish, and inevitably the biases of memory looking back years later.
Exactly. And the very fact that this ambiguity itself has generated such extensive historical debate, including that famous play Copenhagen, really testifies to the immense moral and scientific gravity of that brief, ill-fated encounter between two giants of physics caught on opposite sides of a world war.
The path of that war eventually forced Bohr himself to become a refugee.
Yes, in the autumn of 1943, the situation in occupied Denmark became untenable. Bohr, whose mother was Jewish, faced imminent danger of arrest by the Nazis. He and his family managed a dramatic escape, crossing the Øresund Strait to neutral Sweden, and from there he was flown to England in, believe it or not, the bomb bay of a Mosquito bomber.
Incredible. And it was only upon his arrival in Allied territory that he learned the true state of affairs regarding the bomb.
That's right. It was upon his arrival in Britain that he was brought into the highest levels of confidence and learned the full, terrifying scope of the secret joint American-British nuclear weapons project, the Manhattan Project.
The very project he had thought was impracticable in a foreseeable future was actually already at an advanced stage. That must have been a profound shock.
It was a massive shock, according to all accounts. It instantly shifted his mindset. He realized the weapon was not only possible, but perhaps imminent. This realization moved him almost immediately from thinking primarily about theoretical physics to focusing on political survival and the future of humanity.
And he joined the project.
He did. Upon joining the Joint Allied Project, mainly as a senior consultant offering insights and perspective, he was given a security alias to protect his identity. He worked under the pseudonym Nicholas Baker. By October 1943, mere weeks after his escape, he was reported to be in London, already associated in press whispers with some mysterious new atomic blast invention. He went, in a matter of weeks, from being the revered sage philosopher of the atom in Copenhagen to being a classified government operative, Nicholas Baker, participating, albeit in an advisory role, in the most secret and significant military science project in history.
And it was precisely his involvement in that project, seeing its scale and potential, that crystallized his final, most urgent mission.
Yes, upon learning the true severity and the advanced state of the atomic weapon development, Bohr's priorities instantly shifted. It wasn't just about contributing scientific knowledge anymore, it became about political and humanitarian intervention on a global scale. He determined almost immediately that the very existence of this kind of weapon demanded a radical new geopolitical architecture, what he termed an open world.
This was the birth of his final mission then. He realized that this weapon of mass destruction meant that unless effective measures to prevent its abuse could be universally agreed upon and carried out, permanent, grave dangers would ensue for all of humanity. This wasn't academic theory anymore. It was truly existential.
He apparently viewed this political crusade, this mission for openness, as being equally, if not perhaps even more important than his earlier foundational scientific work that won him the Nobel. His aim was nothing less than trying to establish genuine international cooperation built on a foundation of actual mutual confidence, not suspicion. He believed that the very nature of scientific discovery, which once made cannot be unlearned, required a radical shift in how nations dealt with secrecy, power, and each other.
So what were the practical requirements of this open world doctrine he was proposing? What did this full mutual openness actually look like in practice, especially as the seeds of the Cold War were already being sown?
Bohr argued for, essentially, two monumental pillars of openness. First, he believed there must be universal access to full information about scientific discoveries. The basic science, the fundamental knowledge, the potential that had to be publicly known and shared to prevent fear-driven secrecy and potentially destabilizing surprise breakthroughs.
Okay, open science. That seems reasonable. What was the second pillar?
The second pillar was the truly crucial and incredibly radical policy demand. He proposed that every major technical enterprise, industrial as well as military, would have to be open to international control.
Wait, international control over major industrial enterprises, not just military ones. That is an extraordinary demand. That sounds like suggesting things like large-scale chemical plants or major energy production facilities, even civilian ones, would need some kind of international oversight.
Absolutely. He understood, perhaps earlier than many, that advanced technologies, particularly things like nuclear power, which could potentially produce fissile material for bombs, inherently blurred the line between peaceful industry and military capacity. True, lasting security, he argued, required total transparency and verification across all potentially dual-use infrastructure. It was a breathtakingly ambitious vision.
And he believed that the nations that had pioneered the weapon, specifically the US and the UK, were in a unique moral and political position to take the lead on this radical initiative.
Yes, that was a key part of his strategy. He proposed that they, the creators of the bomb, should be the ones to offer this full mutual openness to the rest of the world, and particularly, crucially, to the Soviet Union, as a first step towards building trust. He felt that this proactive offer of openness, coming from a position of strength but also vulnerability, could potentially cut through the inevitable, dangerous cycle of suspicion, espionage, and fear that pervasive secrecy would otherwise foster.
Did he actually try to pitch this idea directly to the key players, to the leaders?
Oh, he lobbied intensely, using his scientific prestige as leverage. During visits to the United States in 1944, 1946, and 1948, he suggested this initiative directly to top American statesmen, including President Roosevelt shortly before his death, and later to Secretary of State George Marshall. He often used scientific conferences or visits to Los Alamos as a cover for these high-level diplomatic efforts.
He even formalized it.
Yes, he formalized his position in a detailed memorandum, which he submitted directly to Secretary Marshall in June 1948. It outlined the stark choice facing the world and argued passionately for the necessity of this radical transparency as the only path away from an uncontrolled arms race.
But his proposals were ultimately rejected or perhaps deemed politically impossible by the leaders he approached, like Churchill and Roosevelt's successors, particularly Truman.
That's correct. The prevailing political logic, especially as Cold War tensions rapidly escalated, was that secrecy, particularly regarding the bomb's technical details, was a vital, temporary, necessary defense asset, not, as Bohr argued, a long-term catalyst for global insecurity and proliferation. Bohr was arguing that secrecy itself was the primary accelerator of the arms race by breeding fear and mistrust. He was fundamentally ahead of his time, or perhaps just swimming against an overwhelming political tide.
The culmination of these tireless behind-the-scenes efforts was his decision to go public, to appeal directly to the world through the United Nations.
Exactly. On June 9, 1950, with the Cold War now in full swing and the Soviets having tested their own bomb, Bohr formally published his views in a public, open letter to the United Nations. This was his final, dramatic, public plea to the world. He stressed again that openness was not just desirable, but the primary condition for the progress and protection of civilization.
Did he address the UN's own struggle?
Yes, he explicitly noted the difficulties the UN Atomic Energy Commission was already having in trying to obtain agreement on international control measures for atomic energy. He argued that this deadlock actually proved the necessity of shifting the core issue away from haggling over control mechanisms and towards establishing the principle of transparency first.
He argued quite powerfully that without free access to all information important for the interrelations between nations, a real improvement of world affairs was, in his words, hardly imaginable. It was a plea rooted deep in his scientific worldview, the belief that only shared knowledge, openly examined, could lead to progress and survival. He was, in a way, applying the principle of complementarity, embracing the necessary tension of opposing political systems to the global stage, demanding that the destructive dynamic of mutual suspicion be replaced by the constructive dynamic of mutual trust, enabled by transparency. #7 outro. What an absolutely incredible trajectory we've traced today. from that young physicist in 1913, just tearing up the old rulebook of classical mechanics, to becoming this deep philosophical warrior defining the very nature of reality in debate with Einstein, and then finally evolving into an aging, almost prophetic statesman, engaging presidents and prime ministers over the future of human civilization itself.
It really is an extraordinary arc, and Bohr's legacy feels like such a unified system when you look at it whole. It's almost impossible not to see the profound connection between his physics and his politics, is it?
Explain that connection one more time.
Well, in his physics, the principle of complementarity demanded that we accept apparently mutually exclusive but equally necessary descriptions of reality, the wave and the particle, position and momentum. We have to hold both to get the full picture.
Okay.
Then, in his politics, his open world doctrine demanded trust and transparency precisely between mutually exclusive global ideologies, capitalism and communism. Why? Because the stakes of global security in the nuclear age were simply too high to rely on the old dynamics of secrecy, mistrust, and suspicion. He saw openness as the necessary complementary principle to national sovereignty if civilization was to survive.
So he leveraged the paradox he found at the heart of the atom to try to frame the paradox of international relations in the atomic age. The same kind of intellectual rigor he applied to the inherent instability of the classical atom, he tried to apply to the dangerous political instability of the new nuclear world.
Beautifully put. And this framework, this way of thinking, is far from just being historical. We still use Bohr's central concepts, complementarity, the uncertainty principle, the measurement problem, to frame some of the biggest unanswered questions in modern physics. Think about the persistent divide between quantum mechanics and general relativity, trying to reconcile the physics of the very small with the physics of the very large.
Still wrestling with those limits.
We are absolutely still wrestling with the limits of human knowledge and the role of the observer in shaping reality that Bohr first really forced us to confront a century ago. His ideas continue to be debated in fields like cosmology, quantum information theory, even philosophy of mind.
The fundamental questions remain.
They do. Perhaps the ultimate legacy of the quantum pioneers like Bohr, Heisenberg, Schrödinger, and the rest is that they showed us something profound about ourselves. That the limits of what we can ultimately know about reality are intrinsically defined, not just by nature itself, but by the tools, the concepts, and the very context we use to look at it. There might not be some independent, underlying God's eye view of reality that we can ever fully access without fundamentally altering or defining it through our very act of observation.
That is a powerful and slightly unsettling synthesis. But let's bring it back finally to Bohr's grand political project, which largely failed. His urgent call for full mutual openness to prevent a disastrous nuclear arms race in 1950 ultimately didn't unite the nations. So here's the provocative thought for you listening. Given the unprecedented dangers of modern scientific and technological advances, and we're talking now about areas like advanced biotechnology, synthetic biology, autonomous weaponry, truly powerful artificial intelligence technologies that share that same dual-use potential, rapid progression, and globally catastrophic risk, is Bohr's principle of full mutual openness, that radical transparency, now more essential than ever. Or, paradoxically, given the increasing geopolitical fragmentation, the deep mistrust, the rise of non-state actors, is that level of transparency he envisioned simply further out of reach today than it was even in 1950?
It's a deeply troubling question, isn't it? It really demands that we ask ourselves, if the immediate, visceral, existential terror of the atomic bomb itself wasn't enough to force humanity into a new regime of trust and openness back then, what hope do we realistically have now against threats that are often far less visible, much more intangible, harder to attribute, and evolving at an exponential pace? Maybe we need that kind of radically clear-eyed, perhaps even slightly pessimistic, but relentlessly honest Bohrian perspective now more than ever before.
A challenging thought to end on.
Yeah.
Thank you for joining us for this deep dive into the complex life and legacy of Niels Bohr, the quantum architect and the atomic conscience.
A fascinating figure. Until next time.